Let me show you how to be a good Bayesian.
Today, I'm excited to have Teemu Säilynoja on the show, a doctoral researcher and data scientist at Aalto University in Finland. Teemu works within the Bayesian Workflow Research Group, led by none other than Aki Vetari, where he focuses on model validation through calibration assessments and predictive checking. In our conversation, Teemu dives deep into his research on simulation-based calibration, that you may know under the acronym SBC, and visual predictive checking. He explains why these methods are essential tools for validating Bayesian models, how visualizations complement numerical metrics, and common pitfalls to avoid in interpreting these visuals. We'll also explore his recent work on Posterior SBC, a novel approach designed to ensure models are calibrated specifically for datasets at hand, particularly useful when data collection is expensive or limited. A word of caution, you will hear some construction noise on my end for this episode. This is really Murphy's Law in action. I unfortunately had no control over this and I'm sorry about it, but I still kept the episode because, well, Teemu had really great stuff for us. So I hope that you will still be able to enjoy it. This is Learning Bayesian Statistics, episode 135, recorded May 9, 2025.
Let me show you how to be a good Bayesian. Change your predictions after taking information in. And if you're thinking I'll be less than amazing, let's adjust those expectations. What's a Bayesian? It's someone who cares about evidence.
Welcome to Learning Bayesian Statistics, a podcast about Bayesian inference, the methods, the projects, and the people who make it possible. I'm your host, Alex Andorra. You can follow me on Twitter at Alex_Andorra, like the country. For any info about the show, learnbayesstats.com is the place to be. Show notes, becoming a corporate sponsor, unlocking Bayesian merch, supporting the show on Patreon, everything is in there. That's learnbayesstats.com. If you're interested in one-on-one mentorship, online courses, or statistical consulting, feel free to reach out and book a call at topmate.io/Alex_Andorra. See you around, folks, and best Bayesian wishes to you all. And if today's discussion sparked ideas for your business, well, our team at PyMC Labs can help bring them to life. Check us out at pymc-labs.com.
Teemu Säilynoja, welcome to Learning Bayesian Statistics.
Thank you. Glad to be here. Thanks for inviting
I'm
me.
super happy to have you here. That's good. Well, one more people in the Aalto University group is now on the show.
Yes. You are really going to collect them all.
Yeah, exactly. It's like Pokemons. I guess I hope you guys evolve so that then I can invite you back on the show. How do you say?
Yeah.
How would I say? How would I say welcome to Learning Bayesian Statistics in Finnish?
Do you want me to translate also the podcast name? No.
Up to you. How would you do that in Finnish if you had to say that?
Tervetuloa, tervetuloa Learning Bayesian Statistics podcasting.
Okay. Thank you. I will edit that and make it like I was the one saying that. So Teemu, I have a lot of questions for you today because you do so many things. But first, as usual, we're gonna talk about your origin story. So can you tell us what you're doing nowadays and how you ended up working on this?
Yeah. Currently, I'm finishing up my doctoral thesis at Aalto University in Aki Vetari's Bayesian Workflow Research Group. I've been focusing on calibration assessments and predictive checking in Bayesian workflow. So the group is kind of structured so that everyone is focusing on some aspect of the great workflow. And also earlier this week, I happily joined PyMC Labs, so I'm very excited to see what that adventure is bringing to me.
Yeah. That's a great addition to the team, obviously. So obviously, I'm I'm not working there anymore, but I've seen you around. Yeah, that's awesome. I was happy to see that, and I am mostly looking forward to see what magic you'll do you'll do first there. And actually, how did you end up doing Bayesian stats? Like, do you remember when and how you were first introduced to them?
Yeah. My first introduction was during my master's studies. I did my master's in mathematics at Helsinki University, and there was this course for advanced inverse problems, and it just happened to be that year that it was held as Bayesian inversion, I think was the name of the course that year. We had a visiting professor, Tapio Helin, who works with spatial modeling and does a lot of Bayesian side for that. So yeah, but it was a very theoretical course. Didn't do almost any. Well, we didn't do anything computational until the course was over, and then the course had a project work, where we then got to do some X-ray tomography. Actually, like we ourselves got to pick an object and went to a lab and took the X-ray and got the raw data, and then had to code up our own MC sampler in MATLAB and come up with the priors and get to know what was inside the object. So yeah, but then there was quite a break. I continued my master's for a year, and then I studied, went to industry, did some data science in an ad tech company, and then sometime later the opportunity rose for doctoral studies in Aalto and with Aki Vehtari. So then that brought me back to Bayes.
Right. Yeah. And actually, what drew you specifically to what you're doing nowadays, which is mainly, as you were saying, calibration assessments and visual predictive checkings for Bayesian workflows?
Yeah. Well, of course, it has a lot to do with also your supervisor, but I guess you kind of gravitate towards where your interests intersect with the expertise of your supervisor. So personally, I'm quite a visual thinker. I basically need to have a blackboard by me or whiteboard or whatever, something easy to draw on, and then low threshold to also just wipe everything off if I'm not happy with what I wrote there or wrote through there. So that's where the visual predictive checking comes from. I really enjoy like a well thought graph and like how visualizations can aid in communication. But then calibration assessment, so simulation based calibration, which I'm sure we will touch soon more deeply, but that first it came, this Taltz et al. Paper was when I was working on this graphical test for uniformity and goodness of fit paper back in 2020. The original SBC paper, or the first paper to actually call it SBC, was under work, and there you need a uniformity test, and that's where the uniformity test that we were making kind of met and found a use. So that kind of was my first touch to then calibration checking, so assessing the inference in Bayesian modeling, and then yeah.
Nice. Yeah. That makes sense. And I mean, I think indeed it's a good time now to try and dive into a bit more of what you're doing. So can you give us an overview of what simulation-based calibration, SBC, is and why it's so important in Bayesian modeling?
Yeah. So simulation-based calibration, we like to call it simulation-based calibration checking, just to underline that we are not actually doing any calibration, kind of not calibrating the model, but checking if the model would be calibrated, or if the inference and the model implementation together would be calibrated. So it's kind of, you could, in a way, think of it as a check for your model implementation and inference algorithm together, that they are working as you would expect. What I mean by model implementation, especially now with PPLs, so probabilistic programming languages, you essentially, you don't need to write your own samplers anymore, but you define your model in something that's a bit more accessible, and then the sampling algorithm hopefully is already there for you, made by some other brilliant minds. So in simulation-based calibration, we essentially we check that the way you've written your model is actually, like, the goal is to check that you haven't done mistakes in model implementation, and also your inference is working. And how we approach this is that we draw first realizations from prior. You come up with, usually that's an easy part, you somehow randomly draw from your prior parameter values, and then you generate prior predictive data from those parameter values, which is also usually an easy step. And if we step a bit further and look a step a bit further away and look at what we have now, that we have these parameter values and some data, well, this should actually be, if you condition on the data, then the distribution of these parameter values should just be your posterior. So, and what, now we've managed to essentially create a posterior sample without any model fitting. But then, if we want to now compare if our inference is working properly, we actually run the inference algorithm to this prior predictive sample, and we again receive a posterior from our MCMC samples, or from our variational inference, or whatever we use for having this posterior approximation. And now we can compare this to the original parameters that we drew from the prior. And these should be from the same distribution, conditional on the data. We repeat this many times and essentially do some test for this, if it holds that they are from the same distribution. And what has been handy is just to rank the prior draw among this posterior sample that corresponds to that particular prior, and that particular draw, and that particular prior predictive sample. And if our inference is working as we would expect and want it to work, then this rank should be uniformly distributed. So that's where the uniformity test then comes also in, that I was mentioning earlier.
Yeah, and
Yeah.
also, so can you hear that?
I heard, yeah.
Yeah, okay.
A
So
huge, you have a
As-
very large bee in your office.
yeah, exactly. So thankfully that's not that. But as Murphy's law states, anything that can go wrong will go wrong. Well, this is exceptional because they are doing some remodeling of my building, and today was like super calm, nothing, no noise at all. And today, exactly as we started recording, they started piercing the wall, like here, on my balcony. So it's
Okay.
absolutely terrible, and I will apologize for that, but absolutely could not control that. So what I will
No.
do though is I will make my questions as brief as possible, especially when the noise is here. So, so thanks in advance for your patience, dear. Thanks. That's a great presentation and summary of what SBC is. To make that clear, maybe two things. One, that can be done on the prior specification of the model, but then also on the posterior to see that the model is actually well calibrated. And I think you recommend doing both. And then you can go into, well, that very new paper that you have out with other authors, which is exactly about posterior SBC and how to do that. And second, how can people do that? Like concretely, listeners who just listen to you and were like, oh yeah, that sounds good. That sounds great. I definitely want to try that in my models. If I'm using Stan or PyMC or any other PPL, how can I do that?
Prior SBC or posterior SBC or both?
Both.
Both. Okay, everything. Well, for prior SBC, it's quite simple. Like if you can code this prior predictive generation yourself, then you can just basically code it yourself. But also for both PyMC and for Stan, there are already packages. For Stan, there's a package called SBC by Angie Moon and Shi-Young Kim and Matti Modrak and myself, which essentially gives you very good framework for running SBC and also then assessing the uniformity. So also it gives you the framework for doing the actual computation, but also then assessing the results. And then for Python, there's a package called Simuk by Arvis developers, which also does the same, at least for PyMC models and Bambi, and I think some other models too, but now I'm not super certain about that. But that's also there ready. If you have a PyMC model, you can just give it to the package, and it will do run SBC for you and give you some calibration assessment plots already. This might take a bit while because you need to refit your model multiple times. In the R package for Stan, you can do parallel inference very easily. So essentially SBC, you would be generating these prior predictive samples multiple times to get an overall assessment for uniformity, but you can, if you have a cluster or something at hand, you can just put them there, have these simulation iterations essentially run as parallel as you want. For posterior SBC, which I didn't yet even explain, but essentially our new paper, this standard way of SBC that I was now describing has a few issues or drawbacks. Essentially, if you have very vague or weak priors and some nonlinearities in your model, you might have regions of the parameter space in the prior where the model inference is somehow not working. Like you have very pathological parts of your prior space, which you would maybe not even see in your real data. Maybe you would, maybe you wouldn't. But anyway, so prior SBC might give you essentially a false positive, saying that, well, in a way false positive if you then would go and fit your model to data that would not produce a posterior in this problematic area. So we have been developing posterior SBC, which in its simplest form, you just replace the prior from prior SBC with posterior, and you create posterior predictive samples. So you essentially focus in the area of the parameter space that is most of interest to you with your data set. And if you're worried about using all of your data and then creating more data, you can only use part of your data and do essentially some kind of cross-validation, so using some random partitions of your data. But that's in very short the idea of posterior SBC. For posterior SBC, you need to make a little bit of extra coding around these packages. I think Simuk is not yet supporting posterior SBC, but I have had talks with Osvaldo Martin, who is actually the developer for Simuk, so that we could add posterior SBC option for Simuk also. And in the SBC package, you can run posterior SBC by defining your data your data generating process, so that you create the data not from prior predictive draws but from posterior predictive draws. So a bit of hand coding, but at least you are given quite clear pieces on where to do the changes. And in our paper, I also have a GitHub repository with examples on how to do this.
Yeah, and I put that, so these two packages are in the show notes, both for R and Python. So if I understand correctly, posterior SBC is a bit more computationally intensive than prior SBC. Is that right?
Yes, but only by one model fit.
Yeah.
Because you need to have the posterior, and then you draw posterior predictive samples, and then refit to that. And of course, if you have a very large data set and you have your posterior, and then you create posterior predictive samples, and well, the posterior updating usually happens so that you then just give this essentially double-sized data set and fit that. So if your model fitting is scaling badly by the size of your data set, then it might be computationally more expensive, or then you need to not use your whole observation data set. Yeah, but yes.
Yeah. And so do you recommend always doing both prior and posterior SBC?
Not necessarily. Prior SBC, if it's very hard to reason about your priors, like you have a very complex big model, and setting these priors is not necessarily. For example, you have a very large data set, so your data is anyway going to dominate in your posterior, and your prior is kind of not that impactful. Then you could consider just running posterior SBC, and then essentially focusing on your computational time just to the region that you are actually interested in.
Okay, yeah, I see. That's useful, and like these kind of practical advice. And I'm curious also, what are some of the challenges you faced in developing posterior SBC and even prior SBC, and how did you overcome them? Like when you came up with the methods?
Well, I think one of these challenges is then, possibly the inference time. Like you are doing multiple model fits, so sometimes, especially if you are trying to build a model and it's not necessarily the final model, so you're still also in the process of iterating with your models. Stopping to run SBC might not be the optimal workflow. So there you might look at running just very small, short number of simulations, just to get like an idea that okay, so at least everything is somewhat okay. Like you would detect some gross problems quite quickly. But also what we noticed, that like when you're only fitting your model once, it doesn't necessarily impact you so much if the very start of the sampling is slow. But then when you are running 500 or 1,000 refits of your model, yeah. So for example, being smart with how you initialize your MCMC chains might actually come and affect you quite a lot. So in the paper, for one example, I use Pathfinder to get initial states for the chains and then only start MCMC. So it kind of, this requirements for computation kind of gave me challenges that I wouldn't have otherwise considered, but they were actually challenges that you would kind of have anyway if you're fitting your model.
Yeah, no, for sure. I mean, because, I don't think there is that many more challenges anyways because of simulation-based calibration. I mean, the only challenge is you need to feed the model multiple times.
Yeah.
But that's the main bottleneck, right? Because otherwise, like, if you have sampling problems, it's not because of SBC, it's because of the model. So yeah, like, I can guess that, yeah, if you need some form of variational inference to sample the model, then you'll need that also for SBC, right?
Yeah.
So,
but here we were just in, like, kind of running a very short Pathfinder chain to come up with initial values for the MCMC. So we were then anyway in the end fitting the model with
yeah.
yeah.
And how, like, what's your experience doing that, actually? Because I know that's what Bob Carpenter intended when he developed Pathfinder. So basically to use Pathfinder as an initialization for nuts. In your experience, does that help a lot? And in which circumstances?
In this, like, this particular example was a ODE model where especially with the priors, which kind of at first look, they look sensible. So when you're setting the priors, you kind of have, you have reasons why you put the priors you have there. But what happens is that you quite often generate these multimodal posteriors where there's a very large, like in area, very large posterior mode, and then a very small, very high peak in the density. That's actually the one that you would find more reasonable for, like, this was a ODE model for a Lotka-Volterra situation, so predator-prey model. And the very large mode was essentially just the posterior mode for where most of the variation in your data was just measurement noise, measurement error. So not necessarily the mode that you would want to explore so much. So Pathfinder was very good at getting the chains to start and from the mode that gives you a posterior that actually finds these seasonal trends and dynamics between the species. And also, Aki Vehtari has another case study, this birthdays case study, which is if you look at the cover of the Bayesian data analysis book, the 3rd edition, there's a picture from that case study. And there also, they have a big GP model where they do also Pathfinder to get good initial values for the chains.
Nice, yeah, this is super cool, man. Yeah, I can guess how challenging the ODE sampling must have been. And is that actually related to why SBC is also interesting for in amortized Bayesian inference? Can you maybe elaborate a bit on that and tell us even how that's important in these settings?
Yeah, well, amortized Bayesian inference, the reason why we really like SBC there is is slightly different. We were lucky to have Marvin Smith, who your listeners might already know, visiting Aalto University as he actually recently defended his thesis very successfully. He was co-supervised by Aki and Paul Bergner. So he was visiting Aalto, and he's of course an expert on amortized Bayesian inference. So in amortized Bayesian inference, essentially what SBC is good for there is that you don't have for amortized Bayesian inference these convergence checks, these called standard convergence checks that we would have for MCMC, R-hats and such. So how do you know the quality of your posterior for the data set that you then observe when you've gone through all the trouble of training your posterior for your neural network to give you a posterior approximation? Well, then you can run posterior SBC when you have a new data set. When you get an observation for an amortized Bayesian, would you call it amortized Bayesian model, something that you have online already ready to run inference. And in amortized Bayesian inference, of course, the inference part is almost instant. And also making predictions after you have this inference is also almost instant. So then you have maybe 500 times something that's almost instant. Still, it doesn't take too long. So it's very fast to run SBC or posterior SBC. And kind of we don't have the main drawback of SBC in amortized Bayesian inference. And we are also missing some standard good checks for the quality of our posterior. So here, posterior SBC is actually quite useful for checking if your model is calibrated with the new data, or is this perhaps out of distribution observation, and we don't have any guarantees of the quality of the posterior then. Also, prior SBC works with amortized Bayesian inference. Before you see any data, you can check how your parameter recovery, for example, is working.
Okay, yeah. I mean, that makes sense, yeah.
Might have been a lot.
No.
All
what you're saying makes sense. And actually, I think SBC definitely makes a ton of sense. Sorry about the noise again. SBC makes a ton of sense in the amortized Bayesian framework for sure, because you already have the ability to just sample. Once you have trained the neural network, you have the ability to just sample from the posterior distribution in a matter of seconds. Like, it's just for free, so why not do SBC?
Yeah, you've already paid the cost, so you can just reap the benefits.
Right. Yeah, exactly. So actually, also something I wanted to ask you about, because you said you were doing that a lot, and I certainly am also a visual learner and visual thinker. So having a blackboard, having a notepad, always have a notepad with me, blackboard when I can, and like it's really how I think. Also, like when I need to understand some concepts, or else seeing the code, seeing the formula is actually extremely helpful to me. And so you do a lot of work that I definitely appreciate on visual predictive checking. And you've released recently a set of guidelines for visualizations, which I put in the show notes. I definitely encourage people to look into that, because that's awesome. I use that all the time at my work. So the work you do, and also with Osvaldo Martin works a lot on that with the new version of RVs, and he also has these project online of an online book about exploratory analysis of Bayesian models, where he demonstrates all the cool thing you can do with RVs once you have fit a Bayesian model. But first, can you tell us why is visual checking so crucial in the Bayesian modeling workflows? Because there certainly is, at least in the classical machine learning world, much more of an emphasis on statistical metrics, much more than on plots. And And even sometimes I've encountered maybe even distrust of plots because they are visual, whereas metrics seem more objective because, you know, they are numbers.
I see. Like, you are not the one making the interpretation, you just have a number and some threshold. Yeah.
Exactly. Whereas a plot, you always, like, often, I've encountered often people who can be shocked by that, by the fact that in the Bayesian framework we use plots a lot, and that seems very subjective to them.
Yeah. Like, well, like if you're doing kind of by the book, the workflow, you should be having a prior predictive plot even before you look at your data at all. So kind of might be very odd for a more kind of frequentist machine learning side. Well, visualizations, like my view on that, why they are so important, aside, like, instead of just having like some kind of numerical assessments, is, well, a very good example is this Ant-Combs quartet, where you have essentially very different data sets all giving the same summary statistics. Very classical example where visualizations gives you immediately something you were missing with numbers. And then in kind of Bayesian modeling, visual predictive checking comes in two stages of the workflow. Like, as I said, first with prior predictive checking. So before looking at your data at all, you can do prior predictions and see what you are actually predicting from the model, and assessing your priors through that. And then once you have done fitting, then you can do, of course, posterior predictive checking, comparing your posterior predictions to your data, which sometimes is frowned upon because you're kind of double using the data, in that you're not predicting out of sample, but you can, if that's very much a worry, you can do leave and out predictions quite easily. These days you have Sysloo to give you, with one model fit, good approximations of what you would be predicting with this leave and out predictive distribution. And then also kind of on the same, Sysloo also gives you an estimate of how good this approximation is. So that's quite a low-hanging fruit for predictive checking if you are worried for predicting on an observation that you've used in fitting your model. I think I don't remember the original question anymore, but yeah, these were at least the thoughts that the question was raising in me.
Yeah. No, that's great. I mean, I think you answered my question, which was basically, can you explain why visual checks are important? And basically your point is, well, they are important because they don't substitute to metrics, but they complement them. And so you might miss things that if you only look at metrics, you will miss things that you won't miss with plots, and vice versa.
Yeah. Especially assessing your prior predictive distribution with just metrics could be, well, I've never tried that, but that could be quite a challenging task. Whereas visual predictive checking is quite, well, it's quite visual. You see what you're predicting.
Yeah, for sure. So I think it's less of a problem. Like once you're doing Bayesian stats, you have to do prior checks. But I think it's less of a problem for new people in the Bayesian world because they don't have any anchor. Because by definition, they didn't have priors before. So it's not that they come and they are used to doing something with the prior samples. Where the switching thinking might need to happen is when you have the posterior samples, because then you have a whole zoo in the classic machine learning world of metrics, which are like it's a very rich field of the literature, and so here people are more anchored, and you might not always have one-to-one comparison of the metrics. So, like, for instance, the calibration calibration of a Bayesian model, to me, is much more intuitive to the calibration of a frequentist model, because you don't have the binning to do and so on. And actually, now we have the new calibration plot in Arvis, in the new version of Arvis 1.0. In Arvis plots, there is this new calibration plot that I use all the time. And this is super useful. And you can, since it's based on the Bayesian ETIs or HDIs, well, then you can actually interpret it as, well, 90% of the data was in the 90% interval, so this is well calibrated, right? So, in a frequentist model, if I remember correctly, that's not really the interpretation you can make of it. So, there's some stuff like that where you need to be careful how you explain it to stakeholders.
Yeah, and in those cases, maybe that's also kind of you said the mistrust to visualizations. When if that's the case, that your visualization is showing a 95% interval, and then it's not actually what it's supposed to show, or the interpretation is not the first one that you would think of. Yeah, that kind of might make you mistrust visualizations a bit more. Yeah.
That's true. Yeah, that's a good point. Yeah, I like that. And actually, could you summarize your main recommendations on choosing visualization types based on data characteristics? And that question is directly basically making you summarize the blog post of yours that I've well, it's not even a blog post. I think it's a paper you've submitted.
Yeah.
That's still in review, if to the best of my knowledge. So that's in the show notes. But yeah, feel free to tell us the summary of that. You can also share your screen and share the paper if you want for people watching on YouTube. But yeah, basically, can you give us the rundown for that?
Yeah. I don't have the paper right now, so I'm trying my best. But I think the summary, in short, is that we look at that what people usually use for visualizations, and where we find the most common kind of pitfalls or chances for issues. And as you said, the recommendations are kind of based on what your data characteristics would be. If you're looking at continuous data, very often you would use kernel density, like just density plots, or maybe a histogram, which might be very fine. But if your data is bounded, usually the default density plot implementations might give you a little bit of a they don't do very well with bounds, like strict bounds in the most common implementation. There are packages like in our site, there's ggdist that automatically tries to detect if your data is bounded and adjust your KDE to actually do this boundary correction. But if you don't make a boundary correction and you are unlucky enough to use a implementation that doesn't do that, then your visualization is, well, basically what you see is not what you get or what you have. So your visualization is misleading you a bit. The model you're fitting, or if you think of your visualization of a model of the data to summarize what you're seeing, what you're having, that model is biased or miscalibrated in some aspects. And then, so kind of my most important recommendation was just be to think of your data a bit and perhaps use two different visualization methods and see if the conclusion you draw would be different. Because, thinking a bit more. Then if you go to discrete data, discrete is a bit challenging. You have routograms, which would be a good visualization for count data, especially if you have a large range of counts. If you have a very large range of counts, then you could almost very often you can just use a continuous visualization to give you a summary of the data. But then if you have discrete data with small small number of individual states, then most visualization packages, especially for predictive checking, because if you're just looking at your data, then a bar graph is usually what you would use for just kind of a summary of the discrete data if you're using just a 1D visualization. But then once you're doing predictive checking, the bar graph is not anymore very useful. The only information you gain is essentially that is your model doing as well or worse than an intercept-only model, which we saw in the paper also as an example. That yeah.
This is a very good and practical paper. Really, the kind of paper I really love. so thank you for doing that. That's super helpful, and I definitely encourage people to take a look at it, because that's how to make justice here on the podcast. But
and it does actually look like a blog post, like you said, a bit, because it's done in Quarto. It's a HTML page. It's for this Journal of Visualization and Interaction, which has a totally open review process. Like the review of the paper is a GitHub review. Everything is happening in GitHub through issues and such. So we thought that this is a kind of an excellent thing to pursue, this open review, and this kind of more like not to be chained to PDFs essentially, because especially for visualizations, and if you would have any interactions these days, it's quite rare to anyway print your paper or actually read a journal, like a paper journal. So why not use something a bit more feature rich?
Really, people don't read journals anymore. That's weird. Yeah.
At least I.
Yeah, but and actually something I recommend people to do is like printing, because the paper is organized around different types of data. So like every types of data are a new section. So something I recommend people to do that I'm gonna do at work actually, because it's the kind of paper you want to have in your favorite tab. So, but even better, you can like print in A3 each section, so that you have the example of the plots, and so that way you can have that on the walls of your office, and then like each time you work with ordered data, boom, you have the poster right here, and you can use that, or normal data, boom, you have it here. So, and I think this is like, at least for me who really don't like that, that will be super helpful. So I recommend people to do that. I'm definitely gonna do that.
Okay. So anyway, it's going to end up in a physical form.
Yeah, exactly.
Yeah,
and so like for your future papers, think about that, Teemu. Like, how will people consume the paper?
Yeah, I'll try to have a poster format also.
Yeah, exactly. Actually, I think I remember you mentioning, not here, but like I think I've seen you maybe write in this paper that visualizations are kind of like models themselves. Can you explain this perspective, and how does it help improve how you think about predictive checking?
Yeah. Well, this is most clear when you're looking at the density plot, because I would be very surprised if it wouldn't be the case. But when you're making a density plot, you're essentially fitting a KDE, kernel density estimate with Gaussian kernels, running some heuristic of deciding the bandwidth for the kernel, and then plotting the density of that density estimate. So you are actually literally fitting a model to your data. But also, if you think of a histogram, you could think of this as a step function to approximate your density. Also, your data density is just a step function. So in that sense, once you think of visualizations as models fit on your data, then you have goodness of fit tests, and you can actually assess that is this visualization representing my data truthfully, or is there some bias or something that's missing? For example, in the case of boundedness, or maybe you have a data set that's otherwise continuous, but you have some point masses or something like this, and then KDE would not do well with steps or point masses in your data set. So then this is more, we give a recommendation in the paper that's more for kind of people developing the packages for visualizations, because you have quite lightweight checks for goodness of fit. So you could have, when you're implementing a visualization, you could just have under the hood a quick goodness of fit test and give the user a warning if there's something very bad. Let them know that, hey, we saw that you're trying to visualize something that it might be the case that your data is actually bounded or discrete and you're using a continuous visualization. So take this into account, kind of proceed with caution.
Right, yeah. I saw Osvaldo did that, for instance, in the new RVs, when you do some plots, and these are binary data, for instance. I don't remember exactly which plot, but then it will give you a warning if it sees its binary outcome data.
Yeah.
It will give you, it will output a warning and tell you, hey, maybe you wanna, we see you have binary outcomes, maybe you wanna use plot path calibration plot instead of that one. I think it's actually the calibration plot. I don't remember, but this warning is in
most
here.
likely it is. Yeah. We were lucky to have Osvaldo join actually I don't know if I mentioned that, but join the Bayesian workflow group in January. So we've had discussions on like RVs and Baseplot, which I'm then developing also. I've been contributing to Baseplot quite a lot like recently. So yeah, these are kind of being developed in a kind of somehow parallel, but also having discussion with each other. Yeah, and what we've seen as kind of the most common mistake. So in Aalto we have this annual Bayesian data analysis course for, I think, roughly 350 students every year start the course. So it's quite a large course, and then we have a project work for the course where the students go through Bayesian workflow and give a presentation of their data analysis, essentially. And then the default posterior predictive check in currently that you get, which is partly my fault because I need to change it in Baseplot, but what you get for example, BRMS is a KDE plot where you have overlaid your data as a KDE and then your posterior predictive samples, a couple of those as KDEs. And then a lot of these projects have binary response variables. So you would have just zeros and ones, and you have a KDE for that. So you're getting a very odd choice of visualization, and on top of that, you're not getting any additional information aside from just, are you doing better than an intercept-only model? Or are you doing worse than an intercept-only model, actually? Yeah, so in that case, we also plan to have for Baseplot like a warning that, hey, now,
yeah,
this might not be what you want to do.
Yeah, I think that's cool. Yeah. And I think in the future, a warning to try and improve would be the one on the Pareto K shape issue in the compare LuCV function, where it's like, because it's very technical. So I think when users see that, they don't really know what to do as the alternative. It's like, okay, but I don't even know what that Pareto K shape means, so I'm gonna ignore that.
That is, yeah, Yeah, and this is one thing that we also want to do is kind of have warnings that then the warning itself would be quite short, but it would have a link that, hey, for more information, here's a vignette. Go look at the documentation page, and this is where we explain it. Like give an example that this is what's happening.
Mm-hmm. Yeah, for sure. Yeah, that would be helpful. And actually, how do you, in general, I'm curious, how do you approach uncertainty visualization in your projects, and why do you think, and do you think it's overlooked by practitioners or not? What is the state of visualization around uncertainty so far in your eyes?
That's a very good question. Like, it's of course very central for Bayesian modeling, but it's also for, especially if you have a user that's coming from out, like is not trained in Bayesian statistics or doesn't have a lot of experience with probabilistic modeling. So then this might be something that kind of comes as a surprise or as something that's hard to interpret. And that's when thinking of visualizations, it's in general, when thinking of visualizations, it's very important to think of your target audience. Like, for example, in the paper, we don't talk of ECDFs as visualizations for your data, but these are quite commonly used in some fields, and then for that audience, that would be a good visualization. And so in that sense, thinking of visualizations in general is very much thinking of your audience and what you want to convey. And then uncertainty visualizations, yeah, there are some kind of basic, or not very basic actually, some mistakes that you do very easily. Like, for example, you have a predictive model and you show then for continuous predictions, you show the posterior mean and then some central interval around it. And then there was this very recent example of a hurricane in the States, and you do that, and it looks like this massive cone that's going to go over the land. Like, the visualization is not conveying that. Actually, what the model is trying to say is that we have multiple possible paths of these predictions, and it's going to be one of these. So you should be using, instead of this kind of natural default, you should be possibly just giving a like a collection of lines, individual lines, and showing that one of these, it could be any of these. So it's not easy, the topic of uncertainty visualization. I think Matthew Kay, Jessica Hallman, they do excellent work on this topic. Yeah, and I believe at least Jessica Hallman, I think you've had as a guest also.
Mm-hmm. Yes, yeah, I did, and I'll put her episode in the show notes, and I may have had Matthew. I think at least we were in contact. I have to check if I already had him on the show. But
he's a very busy person.
Yeah, we were at least in contact. That's what I can tell you. And actually, what do you? So I'll start playing this out here because I know it's late for you, but I want to pick your brain on the trends that you see shaping the near future of probabilistic modeling, and also where would you like your research to go next?
Yeah, if only I could see the future. I think amortized inference is definitely going to become popular, even more popular than it is now. Like now, for example, for Bayesian experimental design, that's you can essentially adjust your experiment on the fly when you're getting data. So, which would not be possible with MCMC. So there what we have done with SBC, and hopefully other people also come up with good diagnostics for validating then these posterior approximation in amortized Bayesian inference. And
what other cases do you see for amortized Bayesian inference? So like here, that would be like online learning and change of the design analysis, if I understood correctly. Do you foresee any other cases where it will be particularly helpful?
Well, it's not my expertise, but I would say that, well, essentially, when you need to have a very fast posterior inference, which essentially is this online learning or something like quick decision making, and perhaps some autonomous, I don't know, like robots, drone flying, something where you need to be very fast, and it's essentially it's better to pay the cost of computation in advance, and then for me, I would, in my mind, that sounds like a very very good feature to have in your pocket as a modeler, that if needed, if this is my use case, I would have at least some knowledge or some basic ability to also do this, like have a amortized model in my back pocket for that need.
Right. Yeah. So cases where it's worth paying the cost of inference upfront, and then once you have trained the neural network, you will get posterior distributions for free, posterior samples for free. Sorry, and you still have to pay the cost of training the neural network, which can be more costly than training MCMC in some for a lot of models. So like here you have to see if that works in your case, folks, because sometimes it will be even longer to use amortized Bayesian inference than MCMC. So you have to fit the requirements basically.
Yeah, and on the MCMC side, also like with NumPy, for example, now like advances on the MCMC side are also not to be discounted, and also like there's a lot of interesting stuff happening with running a lot of very short chains in parallel, which also sounds quite promising and interesting. Like instead of like usually, I think usually the default is running 4 chains, but what if you run 400?
Yeah, for sure. that's interesting. And actually now you can do adaptation of the chains with normalizing flows in NumPy, and then NumPy will use that as the initialization for MCMC. So these can be somewhat similar, like in the idea to amortized inference. It's not exactly the same, but like basically you would need to train normalizing flows and then use that for MCMC. NumPy does that out of the box for you and under the hood for both Stan and PyMC. Again, it needs to be a model that has a particularly complicated posterior geometry, because you need to train a neural network first. So that's not a complicated enough model for MCMC. It will still be much faster to run MCMC than run the neural network and then MCMC. So it's not gonna always be useful, but for some cases it's gonna be a game changer.
Yeah, knowing which tool to use for which case. Now that essentially the toolbox is getting more and more tools in it,
right?
And it's
that's true. And actually I already had Matthew K on the show. I can confirm that is episode 66 That's in the show notes, folks, so if you want to listen to that. And Jessica Hallman was also on the show, episode 73, and that's also in the show notes. So, yeah, show notes are big for this episode, so that's awesome. I'm happy about that. That's a good sign. Awesome. Well, Teemu, anything to add before I ask you the last two questions? The traditional two questions?
Oh, those ones. Yeah. No, I think you've had very, very good questions. Thank you for those.
Thank you.
Yeah.
I try, but I've had 5 years of training, so that's a good sign that I made progress on that front.
Senior podcast host.
Exactly. Awesome. Well, Teemu, that was great. But of course, before letting you go, I'm going to ask you the last two questions I ask every guest at the end of the show. So first one, if you had unlimited time and resources, which problem would you try to solve? Yeah.
Because I've been listening to the podcast for quite a while now, and I've been thinking that if I would be put on this spot, I would probably come up with a very boring answer of word peace or something. But then now, actually today, earlier today, I was walking my dog and this came to my mind that it's not necessarily such a boring answer to say that I would like to, like we have a lot of problems at the moment in the world, but I would like to solve communication between people. And I think this is in a way also a very Bayesian problem, because the receiver has a latent model of the world, their understanding. And you as a communicator, you should be understanding, you should be kind of able to assess what's that model and then fit your communication to that also. So perhaps, communication, misunderstandings, understanding other people. I wouldn't shoot anything lower than that with unlimited resources.
For sure. Yeah. No, I love that. Yeah, and for sure it's related to priors and how to elicitate priors from people. Yeah, I love that.
Yeah.
Related to basically.
Update the beliefs of the recipient.
Yeah. Related to the Socratic methods in a way, like, for sure. Yeah. Straight epistemology and all that good stuff. Love that, Teemu. And second question, if you could have dinner with any great scientific mind, dead, alive, or fictional, who would it be?
It would be dead. So I have a background in mathematics, and especially in the 19th century and before that, mathematicians had this bad habit of dying very young. So I would pick. I went with this in mind, and I found Gotthold Eisenstein, who was a mathematician in the 19th century, a German mathematician who worked on analysis and number theory, and actually kind of what he managed to do before meeting his untimely death at the age of 29 was he solved issues that then allowed Gauss to further his research. So I would, and also was a very interesting person. Spent a time in prison for some political opinions and things like this in Germany. So then having a dinner and trying to maybe obtain some knowledge from a person who would probably have had a lot more to give to the world.
Love that, yeah. Great. I love that, and you're the first one to answer that. So congrats, Teemu.
Thank you. Yeah, I also thought that it can't be some very obvious scientific mind. It must be some slightly niche.
It can be. That's fine.
Yeah.
Nobody's judging you. Awesome. Well, thank you so much, Teemu. I'm gonna let you go to sleep because it's late for you in Finland. You've been kind enough to to stay up for me to accommodate my my American schedule. So thank you so much.
No problem. It was a pleasure.
Sorry again to you and all of you folks for the construction noises that you must have heard from time to time. They seem to have stopped now, but yeah, like, you know, as Epictetus said, this is a thing in life I cannot control. So I tried to keep my calm. That was not easy, but I kept my calm through the construction noises, so I'm happy about that. And I hope you still could enjoy the episode. Thankfully, Teemu was the one with many more things to say than myself, so not too much construction noises on your end. As usual, I'll put resources and a link to your website and socials in the show notes. Teemu, feel free to add anything in there also if you think I missed some. And thanks again for taking the time and being on this show.
Thank you.
This has been another episode of Learning Bayesian Statistics. Be sure to rate, review, and follow the show on your favorite podcatcher, and visit learnbaystats.com for more resources about today's topics, as well as access to more episodes to help you reach true Bayesian state of mind. That's learnbaystats.com. Our theme music is Good Bayesian by Baba Brinkman, feat. MC Lars and Megaran. Check out his awesome work at bababrinkman.com. I'm your host, Alex Andorra. You can follow me on Twitter at Alex_Andorra, like the country. You can support the show and unlock exclusive benefits by visiting patreon.com/learnbaystats. Thank you so much for listening and for your support. You're truly a
good Bayesian. Change your predictions after taking information in. And if you're thinking I'll be less than amazing, let's adjust those expectations. Let me show you how to be a good Bayesian. Change calculations after taking fresh data in. Those predictions that your brain is making, let's get them on a solid foundation.